Alright, so the basic idea that I'm looking at is trying to treat basically every single function the same. So instead of this whole like all of our going through all of our what are sometimes called toolkit functions, or I call them parent functions. Um, and instead of taking them and saying like, oh well, parabola is graphed this way, and an exponential function is graphed this way, and when you do stuff to it, it does different things. I've been formulating a way to just make it all exactly the same, and as long as you know what the parent function looks like and you know what function transformations are being done, it takes about 30 seconds to graph even the hardest stuff. So what I've been looking at is saying, you get your basic stuff, y equals x, y equals x squared, y equals x cubed, so all the polynomials. And roughly speaking, these are going to be identical when you graph them. It's just a matter of like trying to find which ones. Going beyond x to the third is also a little ridiculous, just because at a value of 2, x to the fourth is 16. So like I'm not graphing that. That's generally speaking. All right, so y equals square root of x, y equals cube root of x, and you keep going again, but again, we don't. This is pretty much as far as we go with that. Let's see, what else do we do? Rationals. Yeah. 1 over x, 1 over x squared. I guess just exponentials and logs then. And then we start getting into trig functions beyond that. All right, so all 6. All right, so what I'm doing with this is I'm saying, all right, let's just graph the basic parent function for any one of these. So if we start with something easy, absolute value, I guess. We do that one too. It's okay. If we just start out with the basic stuff, so y equals x is going to have a basic scheme that everything that's on the left is just also on the right. Right? This is not a difficult function. And then you all are given the opportunity to check out some interesting stuff by saying like, when we graph, or after we graph this parent function, we want to start looking at stuff like y equals 3x plus 4. Come up with anything you want. And what do all of these individual transformations do to the parent function? Well, first of all, we've probably all done this increased the slope, so 3 times x makes it 3x, makes it steeper than the original one, y equals x. So this is a vertical stretch. All right, and then this 4 here also moves it up 4 spaces. So this is the same as doing a vertical shift. All right, all well and good. Easy enough. We have a vertical stretch factor of 3. We have a vertical shift of 4. So a lot of times what my colleagues will do is just, there you go, there's your B, you jump up here to 4, you mark it, and then you do 1, 2, 3, 1, 2, 3. uh, up 3 over 1, up 3 over 1, and you just keep going, and that's it. So I started looking at this, and some of my students weren't terribly happy about um, their understanding of why this all worked. I mean, not necessarily with linear functions, but when we start getting up into the higher stuff, logs, exponentials, rationals, even just polynomials and roots, they're like, I just don't really see where I'm going with this. It doesn't make a whole lot of sense necessarily. So I said, all right, let's think of this as your original function has the origin point, 0, 0, as the place where it's starting from. Then what we're doing is we're looking at the original parent function, which went, up over 1, up 1, and repeated. 3, 4, 5, 6, 7, 9, 10. So the original parent function went like this, and it was just literally whatever your x is, your y is also. Right, so we get this thing. It's totally straight. Don't worry about that. All right, y equals x. So then what happens is that our transformations, as we've written them, this is a vertical shift. I actually started with the shift first. And I said, okay, my origin point, the place where I'm starting this graph, is getting shifted up 4 spaces. And then from here, the usual scheme is that 0, 0 is our origin. We then go right 1, up 1, right 2, up 2, right 3, up 3. But the vertical stretch factor is going to affect our vertical distances. These are going to be the vertical distances from the new origin point. So this point, 0, 4, is our new origin point. So 0, 0 is going to land us still at 0, 4. Then, again, we triple our y distances, our vertical distances. So instead of going over 1, up 1, we now go over 1, up 3. This is now our point here. Now, I know a lot of you are probably like, well, yeah, don't worry, we're getting there. Over 2, up 6. Over 3, up 9, etc. All right, well, that also means that we can go in the opposite direction. Left 1, down 1 now becomes left 1, down 3. And left 1, down 3. Left 1, down 3. It's now going to be over here. So this is y equals 3x plus 4. Now here's the thing, that doesn't have to be the only way you think about this. It doesn't have to be y equals 3x plus 4. We could also alter this just a little bit. If you were to factor out this 3, this would be x plus 4/3. We could do this still as a vertical stretch factor of 3, but now inside, because it's affecting the x first, this is a horizontal shift. Of negative 4/3. So our horizontal shift, the origin point on 0, 0, now shifts left 4/3 and marks out this point. This is negative 4/3, 0. Okay, now if this is a vertical stretch factor, we can still say, okay, we're going to go over 1 and then up 3. So this is going to be at a value of negative 1/3, we're going to reach 3. And then at a value of 2/3, we're going to reach 6. And so on and so forth. We could think of this in a slightly different way. The items that affect an the items that affect yeah the items that affect an x value on the inside of the function are going to be doing things to the horizontal direction. All right, let's say you don't like that. Okay, I can go one further. I could even say, okay, what? Oh no, am I in the way? No, okay. I could even say that this could be y equals parentheses 3 times x plus 4/3 like this. Now, the outer parentheses don't technically do anything, but it is a note-keeping way to say, well, wait, what if this 3 was a multiplier on the inside of the function instead of on the outside of the function? Well, that is going to cause the horizontal direction. You're going to effectively be looking 3 times further for a particular x value's corresponding value in the parent function, and then bringing that value back. So what that's going to do is we're now going to look at taking a function that is like this big and then crushing it down to only being this big. So this is a horizontal compression factor. And our plus 4/3 on the inside is still a horizontal shift of negative 4/3. So what does that do? Well, that changes our axes. Instead of worrying about this being in whole numbers, instead of this being whole numbers, we're actually going to look at this in terms of being cut into thirds. So if you subdivide and think of the distances now in terms of thirds, we shifted left 4/3, so our origin point is now here at negative 4/3, 0. Then we're going to go over 1/3, up 1. Over 1/3, up 1. Over 1/3, up 1. Over 1/3, up 1. And we hit all of these points that we have hit all along the way, including some extras in here that I didn't do from other versions. So our x units now are counting by 1/3 instead of counting by ones, and our y units, the vertical distances from the new origin point, are going to be counting ones still instead of threes as we had been doing with the vertical stretch factor of 3. So you can think of this in practically any way that you want in order to say, like, how can we graph this particular function? In the case of the identity function y equals x, right, your horizontal and your vertical shifts just have to you just have to do a mental shift in order to say, oh, they're the same thing. The vertical stretch and the horizontal compression are literally the same thing because you're either multiplying on the outside or multiplying on the inside, and it's the same thing because there's nothing separating those parts. So when we're looking generically at all of the parent functions, our function transformations look like y equals a times f of b of, or b times, x minus c plus d, where a is a vertical stretch factor, b is a horizontal compression factor, c is going to be the horizontal shift, and d is going to be the vertical shift. That one's awfully close. All right, just give me 1 minute here. Be right back. All right. So, like, everybody's probably seen this or something very similar to it. And well, that's annoying. There we go. Okay. I was going to say you can't see my cursor. That was awful. I just didn't have the window highlighted properly. Okay. So everybody's probably seen like some version of this at the very least. Let's get rid of this. And depending on the kind of function, there might be some sort of relationship between these four things. The one that I like to use most often when I'm just talking about like this thing will not have any sort of similarity when you multiply 2 as your a value, then it will not affect any of the other things at all. I guess I shouldn't technically say that. Like b and a can sort of be similar, but you have to do a little manipulation. So in the case of like our square root function, right? If we do y equals 3 square root of 2x minus 1 plus 1, just throw something out there. Right, I can graph this pretty quickly, all things told. I already know, for instance, this is going to shift right 1, up 1, so that should be really down here. No. That's not even on the board. All right, so this is going to be 15 here, 10, 5. 1, 2, oh no, wait. Because we're horizontally compressing our x values and vertically stretching our y values, you probably want to. So I don't know if anyone has taught this, just because, like, I don't know. Like, I used to teach the ABCD thing, and all of my colleagues did too, but it was a lot of like, here's how these exact same things apply to a new function, but you're just like trying to relearn it again, and it seems a little ridiculous. And students would also like constantly try to make tables with the same points. Yeah. So they constantly try to make tables with the same points, like -3, -2, -1, and they don't work. So why would you want to do that to yourself? It's just a lot extra work to do that. So instead, what you should do is look at what happens to the important points. So the important points, the parent function points for square root of x, y equals the square root of x, are going to be the perfect squares in for x, and then the so 0, 0, 1, 1, 4, not 2, 4, 2, 9, 3, 16, 4. All right, and here's where I differ from the rest of it. These are my distances. Like, nobody that I know teaches it in terms of thinking of it as distances. They're always like, let's just find a point that's going to work. You don't need to find a point that's going to work. You can think about it a little, maybe it'll work, but you can also come over here and say, what I'm doing is I'm going to take the original parent function from 0, 0. It's now going to get shifted up 1 and right 1. All right, 5, 10. All right, new origin point is 1, 1. This is also a point on the graph, 0, 0. Then what we do is we say, okay, the next point would be 1 over 1 up. But now it's going to be compressed a horizontal distance of a half. So now it's only going to be a half away in the x direction. So 1.5. By then the y direction is being stretched by a factor of 3. So now it's a half by 3. So over a half up 3 is going to get us to here, 1.5 comma 4. All right, 4, 2 is now going to be halved in the x direction, so it's only going to be 2 away as a distance. And now instead of 2 up, it's going to be 6 up. So again, triple our y distances. So 6 up from here, 2 away, 1, 2, 3, 4, 5, 6. So this is going to be 3, comma 7. This is 3 halves, comma 4. This is 1, comma 1. All right, we're going to get one more out of this. So 9, 3. Actually, we can. No, we can't because it doesn't. Anyway, 9, 3 is going to be, again, 4.5 distance from 1 is going to be 5.5, and then this is going to be an extra 3 up, essentially, is what's going on. With the square root function, you're incrementing in the y direction as opposed to the x direction like the parabola, which, again, all you're doing really is looking at the inverse function of this thing. And you got something that looks like that. I guess if we wanted to, right, this is going to be 8, comma 12 as distances. So again, 8 from 1 is going to make it out to 9, and then 12 from 1 is going to make it to 13. So like 1, 2, 3, somewhere up there. Close enough. So yeah, I do everything as distances, and it makes it, I think it makes it more intuitive. I don't know about anybody else, but And the other thing is, if you don't like what's on the inside here, or you don't like what's on the outside here, in the case of the square root function, you have a way to change it. So if it were like, 3 square roots of 4 times x minus 1 or whatever, this, you could take the square root of 4 and make it 6 root x minus 1. Just, you can manipulate it. That's not what is actually here, so I'm just going to get rid of that. Destroy all the evidence. And if you want to look at like how crazy this can get, we'll talk about rational functions. So everybody kind of hates on rational functions because they're weird and they got asymptotes and things like that. But you can look at this and say, okay, y equals 1 over x is going to be the parent function, which also means that x times y equals 1. And I don't care even what this number is over here at all. Nope. All right, so if I trade this for some crazy like transformed function, I can make this turn into y equals 3 over 2x plus 1 minus 4 on the outside like that. Now, if we want to think of this as a transformed 1 over x function, all we're doing here is we have a vertical stretch of 3. This is a vertical shift of negative 4, so it's going to go down 4. This is going to be, again, we have to factor this into 2 times x plus a half. Yeah, I got you. See you later. Have fun. All right, so a 2 here is going to be a horizontal compression. Yeah, no problem. And then the plus 1/2 is again a horizontal shift to the left a half. Yeah, see you, Soul Reaver. Have fun. So what does that mean for us? Well, we're going to make something that's slightly off-centered. Our original y equals 1 over x function has its origin point still at 0, 0. However, the function doesn't go through those points, or doesn't go through that point. The function goes through 1, 1, 2, a half, 3, a third, 4, 1/4, etc. And then this way it goes to 1/2, 2, 1/3, 3, 1/4, 4, etc. So we got these asymptotes. They're going to be along the axes. So y equals 0 and x equals 0. Close. And then we got the same thing on the other side for the negatives. All right, now, if I'm going to do a vertical shift, then I'm going to take the horizontal asymptote and I'm going to shift it down. Not very even, but whatever, it'll work. All right, we got this way 1, 2, 3, 4, 5, 6, 7. These are awful rough sketches, but it'll work. All right, did you ever want to know how this thing works? Well, look at y equals 1 over x, forget the reciprocal thing. Look at this in terms of distances. Whatever your x distance is, your y distance has to be the reciprocal of it in order to get 1 back. This function, although not exactly the same, has pretty much the same properties. If you are going to double your x value, whatever your x value is, if you double your x value, you have to balance it by halving your y value. So the same thing happens over here. You take the x distance from the origin, which in this case is 1 to get to here, you double it to 2, and that causes you to halve your y value. It goes down to a half. All right, take that point. Double its x value to 4. That's going to cut its y value in half again. Half of a half is a fourth. Well, the same thing happens on the negative side. You're starting at -1, -1. You have the x distance, you double the y distance. You have the x distance, you double the y distance. You have the y distance, you double the x distance. Have the y distance, double the x distance. All right, forget the 3's over here. I was doing that kind of just out of habit. We don't need to do them. So really, all you need are powers of 2 when you're talking about rational functions in general. All right, so our original point is now being moved. We have a horizontal shift of -1/2, because again, it's the opposite of what we have in there, by -4. So this is our origin point, which again is not used in the function. From that point, from the origin point, our initial point for the rational function is 1 over 1 up. Okay, now we have a horizontal compression factor of 2, so that 1 is now getting compressed by half, or by a factor of 2, into a distance of a half. So our initial point is going to be only a half away, so now we're back at 0. Then it's going, the y value, y distance, will be tripled. So instead of over 1 up 1, it is now over a half up 3. So over a half up 3 gets us the initial point on the positive side. Now it's also true we should put in the vertical and horizontal asymptotes at x equals -1/2. Oh, that's going to be lovely. And y equals -4. All right, so x equals -1/2, y equals -4 is going to get us our two asymptotes for this particular function. Then what we do is we say, guess what? Once you have the initial value here, we don't need anything else. You just got to go back with the same scheme that we had up with the rational functions, which is we take this distance, which is 1, 2, 3, to the asymptote, or to the origin point in the y direction, and we halve it. So 1.5. Now we take the x distance and we double it. So a half now becomes 1. So now we are at 1, comma, -2.5, or -5/2. If you want to know where the locations are, you can always figure it out. But quite frankly, I don't care. I would rather my students understand the scheme of how all this stuff works and not have 100% accurate points, if I'm honest. All right, this point was 1 away from the axis, or from our vertical asymptote in the horizontal direction, and so now we can double it to a distance of 2, which causes us to have this y distance again. Technically, it's going to now be, instead of 1.5, it's going to be 3/4. Again, Doesn't bother me all that much. You can figure out where a half of a distance is very easily. You can figure out the numbers slightly less easily. So we know that this is here. It's half this y distance here. So mark it out, bring it over. We can double this x distance from 2 to 4, and then cut its y distance in half again. And then if we go one more, it's going to be off. All right, same thing when we go up. We could cut this distance from a half to a quarter, and then double its distance from 3, 4, 5, 6 to 6. So we're at negative a quarter, comma 2. All right, and then this is a matter of just being nice with the freehand. That's awful. So be careful when you're graphing it. Oh. All right, let's do the artist thing. If you make many lines, then you don't have to undo all of your lines. Okay, and that goes vertical, almost vertical. All right, on the negative side, we've got the same thing. So go over a half, which brings us to negative 1, and then we go down 3. 1, 2, 3. Again, triple our original y distance, which would have been 1. So over a half, down 3, gets us to this point. Then, again, you go half the x distance, you're going to double the y distance. So 3 now becomes 6. So this is negative 3/4, comma negative 10. All right, and then if we had gone, again, from here, we can halve this distance to 1.5, and then double its x distance to the next whole number over here. It's going to be a distance of, oops, hang on. I might have gone a little bit far. I'm going to mess that up. Nuts. Okay, hang on. All right, so if we're here, we're at a distance of a half. If we double that, we're at a distance of 1 from negative a half is going to be negative. Yeah, I messed it up. All right, so it's halfway in between. This is negative 1.5, comma negative 5.5. On the other side, this also means that these are all wrong. So hooray. This is going to be actually here. These are all dragged back a half a point. They're all off by just annoyingly enough. But if you make your lines really thick, nobody will notice. All right, halve this distance again and double this distance. So this distance is a 1. It's now going to be a 2. Halve that y distance. Halve the y distance, double the x distance out to 4. Again, you can mark out as far as you want to go. All right, we get all those points in. Awesome. All right, did we get anyone new in? Let's see. Twitch details. Well, welcome. Okay. So, if we've got rational functions like this, this is going to allow us to, again, think of this in terms of distances instead of like actual points, and it's going to help you understand how all of this works. If you wanted to, This is not a like requirement or anything, but if you wanted to, you could also take this as y plus 4 equals 3 over 2x plus 1. Multiply your 2x plus 1 on both sides. This is 2x plus 1 multiplied by y plus 4 equals 3. And now you can see, again, if you double your x term as a whole, you're going to have your y term as a whole, and vice versa. This changes a bit when you go to like y equals 1 over x squared, because this is now x squared y equals 1. If you double your x term, it's going to square that doubling. Sure. Like 10th grade algebra-ish, or geometry. Or are we talking like calculus level? So that might scare me. All right, anyway. So to wrap up on this, anytime that you're doing function transformations like this, if you think of it in terms of distances, it makes it so much easier. Okay. Well,